Welcome, 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 welcome to Astronomy on Tap. It's great to see everyone here. Thank you for coming. Welcome to our fourth Astronomy on Tap. My name is Yair, and I'm happy to have Griffin Hossenzadeh here with me, who's a grad student at UCSB. I'm a postdoc there. We both work at LCOGT, local observatory here. And so if you've been here before, we'll be doing things a little bit different this time, just a little bit different. We're going to have our first presentation, which will be Rob, about planets. And we're going to take a break right after that. And so if you have questions for Rob, you can text them during his talk and the break to this spectacular phone number that we landed, 805-55-AOTSB, okay? So just keep that phone number in mind. If you have questions during the talk, you can text them, and then we will answer them when we come back from the break.
And I discovered in setting this up that if you have an iPhone, you can just type the letters in as the phone number, and it totally works. That's the magic of Apple right there.
Yes. So when we come back from the break, we'll answer the questions we got from you guys by text, and then we'll do Astronomy in the News. We'll take another break. We'll have our second presentation from Charlotte about galaxies. And again, during that talk, if you come up with a question, you can text it, and or during the break after that, and then we'll answer it. And we'll end by raffling our world-famous Astronomy on Tap beer glasses, which you can get. So you should have a raffle ticket that you got at the entrance. If you didn't, who are the raffle tickets responsible people here? Okay, so if you didn't, go get one during one of the breaks. So you need a raffle ticket that says Astronomy on Tap and has a number so that you can get in on these glasses. Okay. Yeah, you wanna?
Yeah, so like Yair said, this event is organized by Las Cumbres Observatory, which we call LCOGT, Las Cumbres Observatory Global Telescope Network. If you want to find out more about us, there are people in the back with brochures, and they're happy to talk to you. We're a local organization based in Goleta, and we operate a network of telescopes around the world to do cutting-edge astronomical research. And people wearing these glow necklaces are scientists and or engineers at LCOGT, so feel free to talk to them throughout the night. We're happy to answer any questions you might have.
Yeah, and we invite you to stick around after the event to talk to the glow necklace people about anything you heard tonight or just were curious about. Okay, so our first speaker is Rob Siverd. He's an instrument scientist at the observatory. What this means is he's one of these rare people who do science and build the instruments that allow everyone else to also do the science. So he does, his scientific area is finding planets around other stars, and he's building an instrument right here in Santa Barbara that's going to find a bunch of planets around other stars and possibly the next, the next Earth planet. So that makes Rob one of the busiest people at the observatory. Like, really, this guy is very busy. So I want, just to illustrate that, show you a picture I took of his desk. So there's a lot going on here, right? So I annotated a few of this stuff. Okay, so I'll give you a second to look at that. Well, okay, so this is a real, yeah, he didn't know we were doing this. Yeah, okay. So let's welcome Rob.
That's fantastic. All right. And I'd like to add to that that is a mechanical keyboard so that I can type even faster than normal people and save what little time I have left. One additional thing, when you send questions, we're going to answer questions about planets and exoplanets. So let's try keep the discourse on that topic. I know some of you out there are planning to ruin me, so don't think you can use our text message line to do that. All right, so today I'm going to talk to you about discovering new planets around other stars. Let's get started. Let's start with a review of where we live now. So this is our solar system and the major objects that you can find in it shown to scale. Scale in terms of the size of the objects. So off on the far left, you obviously have the sun. That's the thing that produces all the energy. Then you have 4 little teeny tiny dots that you can barely see here. Those are the inner planets, Mercury, Venus, Earth, and Mars. Then you have Jupiter and Saturn, our friendly neighborhood gas giants, followed by Uranus and Neptune. Additionally, there's a bunch of other things that just barely missed the cut. So Pluto used to be a planet, as many of you probably know, and you grew up thinking it was a planet just like I did. It's been demoted for good reason. It turns out it's one of like 500 things, and otherwise we'd have to come up with names for 500 things, and no one has time for that. So it's been demoted to dwarf planets, along with some of its neighbors, Haumea, Makemake, and Eris, which are named after various types of mythologies. There's also Ceres, which is a failed planet that lives in the asteroid belt over here. This is what our solar system looks like to scale in terms of distance from the sun. So it's a very, very different picture. Some of you may have participated in our recent Bike the Solar System event. And so those of you who did probably already know this. But the inner planets live very, very close to the sun. Then you find Jupiter and Saturn, and then there's this huge gap until you get to the ice giants, Uranus and Neptune, and then Pluto. The next thing I'd like to point out is that, and sorry for the brightness here, our solar system is actually flat. It's like a big frisbee around the sun. The inner here, I don't know why it keeps fading out. The inner few planets are right here around the sun. You can see them in the bottom right-hand corner here. They're all orbiting in a really, really flattened disk, and that remains true all the way out to Neptune. Pluto is, and this is part of why it was demoted, is breaking with tradition and is hauling way outside that flattened disk. So the inner planets are small and rocky. You're familiar with most of these. They have solid surfaces. One of them has a breathable atmosphere that is conducive to astronomy on tap. And some of the other ones are close, but not quite. The outer ones are much bigger. Again, this is Jupiter and Saturn and Neptune and Uranus. It's not a coincidence that the inner ones are teeny tiny and made of rock, and the outer ones are big giant balls of gas. So it turns out, or so we thought until about 20 years ago, that the reason that we had this situation was that rock was the only thing that can withstand the heat of the sun, and that's why the innermost orbits are all, or the innermost planets are all made of rock, and the outermost ones are cool enough that lighter gases can accrue and form these giant planets. It turns out that this is sort of partly true, but not quite in detail. So what are exoplanets? So exoplanets are just planets around other stars. They are pretty interesting because they give us some insight into some really fundamental questions, like how did we get here, and are we alone? Those are some of the driving questions that at least motivate me to keep after this. Those types of questions can only be answered indirectly, and the way that we do that is by looking and seeing what nature has provided and figuring out what the underlying physical principles are, and therefore, and once we understand those, or we think that once we understand those, we'll be able to predict better, the answers to questions like, are we alone? And we can also figure out things like, where might we find life elsewhere in our solar system? Where might we find life elsewhere in our universe? Which is hopefully something we'll identify during most of our lifetimes. The plot here that I've shown goes from about 1990 to 2014, and it shows the number of exoplanets discovered every year since then. And the main takeaway point here is that the number is growing really, really fast. So the first one we discovered around a sun-like star was found in 1995, way back over here. And then it turned that discovery more or less upended our view of how of what might actually be out. Upended our view of what might be out there in the universe. Since then, we have produced a whole bunch of new instrumentation that's capable of finding what nature has actually provided. But we were delayed in finding those because of our own prejudices based on what we see in our solar system and the belief that our solar system was common. How do we find exoplanets? So the first and simplest method is just looking. So Yogi Berra has this famous quote that you can learn a lot by just looking. And this is true. So most of the planets that we know about in our solar system were found this way. People point big telescopes in directions where we expect to see them and look for things that move, and then you find them. This is an observation that I took using a telescope about 45 minutes north of here up in San Ynez of Jupiter over the course of about 4 hours. And these little dots around it are its moons. And so this is kind of analogous to a star-planet system, and you can see that maybe when you look at these things, you'll see things moving, and you'll say, wait, wow, there's things orbiting around them, and there you go, done. This does actually work for some exoplanets. So this is an example of such a system that has 4 known planets in orbit around it. And all you have to do is, step 1, get lucky. Step 2, have a giant telescope and really awesome weather. And then step 3, stare for a while. And what you'll find is that you might actually have some planets around here, and you can see them move, and you can confirm them this way. Here's another example of such a thing from the Hubble Space Telescope. So ignore this giant circle eye-looking thing in the middle. That's actually an artifact of the camera that they're using. But the important part is here, and if you have enough patience and are willing to wait 10 years, you can see the planet move and say, oh, hey, there's a moving solid object there. The problem with this method, this direct imaging method, is that it takes, you need 10 years and giant telescopes and billions of dollars, and that's really not effective. The second method, which has really taken off in recent years, is the transit method. So this is a schematic of what's happening. The orange dot, it represents a star, and the black dot represents a planet. And a transit is simply astro jargon for a small thing passing in front of a big thing where the small thing fits entirely inside the big thing. So it's basically a partial eclipse where the smaller of the 2 objects is enough smaller that it fits inside the larger of the 2 objects. Some of you may remember there were some recent famous transit events in our own solar system in the past decade or so. So this is a picture of the transit of Venus in 2004. You can see Venus is the black dot here down in the lower right corner. It, a bit of the light from the star is blocked, and you can see it pretty clearly. If this were a video, you would see it marching right across over the course of like half a day. Earlier this year, we saw the transit of Mercury. Mercury is right there, and I think I don't know if you can see it that well. Got this trusty pool cue. It's right about there. It's not the biggest of the black dots, so some of these other black dots are actually star spots on the surface of our sun. The sun actually knows we're trying to find planets and is making it difficult on purpose. And the other thing worth mentioning is that, so this is Venus. Venus is much bigger, if you remember my earlier slide, than Mercury, and consequently the shadow that it casts is also much bigger. So the size of the silhouette is actually very informative to us. So when you look at other stars far away from our sun, you can't actually resolve the disk. So instead, what we do is we just add up all the light coming from the star, and you use the total amount of light coming back, the total brightness, as an indication of whether or not something is passed in front. So this is a schematic of what happens. A planet passes in front of a star, and what you see is a little dip in the light. The disadvantage of this method the transit method is that you have to get lucky. So not all planets will transit their host star as seen by the Earth. If the orbit is aligned edge-on, as in the upper left here, then sure, yeah, you see a transit. If it's close enough to edge-on that it kind of crosses, then yeah. But if it's face-on, you see nothing. And if it's, just a bit outside of just tipped enough, then you also see nothing. So you don't actually get to see this effect for all planets that exist. How do you compensate for that? So there exist a number of surveys, both in space and on the ground, that have found a bunch of these planets. And for about 10 years now, I've been working with one called KELT, the Kilodegree Extremely Little Telescope. That's not a joke. It's actually true, and you'll see in a minute why we call it that. Anyways, this is a field of view, and what you do to compensate for the fact that these things are rare is you look at a gazillion stars all at once. So in one of our typical images, we see 100,000 stars, and we can monitor them all at the exact same time. And that makes it a ton easier to actually find things that are rare. So if 1 in 100 planets has a big giant Jupiter-sized planet that's in a close orbit, and 1 in 10 of those has the right alignment where you can actually see it transit, you're in luck because there's going to be like 10 or 50 of them in this field that you looked at. This is what the KELT telescopes actually look like. I'm not even joking. We got our optics on eBay. It's literally a sort of SLR camera type lens with some duct tape and tinfoil around it attached to a digital camera. And it is to this day miraculously running with Windows XP. We have not installed any updates. I have converted them to solid-state disks because they're not allowed to die because they can't be replaced. And it's just a mess. But it turns out they actually work. So we put these things together for like $50,000, and they live in these glorified sheds. So KELT North is in a guy's backyard in Tucson, Arizona. And I'm not even joking. He has a really nice backyard, though. The KELT South is at a major astronomy facility in South Africa. So it's sort of an upgrade. And it has its own private shed. It doesn't have to share the shed with other telescopes like our Northern telescope does. Here's a video of what it actually looks like when it's running. So this telescope has a bit of ADD. It can't focus on any one thing for more than 3 minutes, and then it's got to move. But this is what it looks like basically when it's running for an entire night. It just snaps photos of a bunch of different places and goes around between a set of predefined fields. And then we analyze those later and try and dig the planets out. So what we found, we've actually successfully found something like 20 transiting exoplanets. And this is what they look like. The data's a little bit ratty, but it's good enough. So what you see is time is going left to right and brightness going top to bottom, and there's a dip. And this looks more, it's not quite as clear as what you would see in the idealized model that I showed before, but it works just fine in practice. We use bigger telescopes to follow these up, and then we can publish them as confirmed exoplanets once we have the right follow-up information. So I'm going to start now and do a live demo illustrating the orbit and viewing angle issues for transiting exoplanets. It's like comparably high tech to our telescope, so don't worry about it. All right, I've turned on the star here. It's pretty convenient. I can just turn this on and off at will. All right, now let's get it spinning. Okay, so this is more or less how an orbit works. So the thing that I hope you want to take away from this is that the people downstairs, when they look at this model, will be able to see the planet, which is the green foam ball, passing in front of the star, which is the paper lantern. Whereas the people upstairs will not actually see this thing transiting. So this is really to hammer home the fact that even if the planet is there, only a select few get to see it through this method. The other thing that you should notice, because this will be important in a minute or two, is that the balance point is not on the star. It's not quite true that the planet orbits the star. It's more correct that the planet and star both orbit the center of mass. It's kind of like a seesaw in that way. Good. All right. Okay, here we go, I found it. All right, so here's an animated GIF that shows basically the same thing from a top-down view. So radial velocity is the second detection method that I want to talk about, and we use the Doppler effect and the fact that the star is moving when there's a planet orbiting it to actually prove that the planet is there. So here's... So many of you have probably heard something like this before, some of you more than others depending on driving skill, but the idea is that the Doppler effect is when you have a moving object that's emitting some kind of wave like sound or in fact light, the frequency or the pitch of that wave is modified according to the speed that you are traveling. Okay, great. So how does this apply to, we actually have a better demo of this. Here we go. This will be really fun. So what we have here is a constant tone generator. So hopefully you can all hear that this is both A, annoying, and B, at a constant pitch. Fabulous. Nice. That concludes the extremely dangerous portion of the demonstration. No one died, and we're happy about that. I was sort of slightly afraid that the speaker would go flying off into the audience and maim somebody horribly, and I would become to be known for that. Anyways, so hopefully you all heard that. That demonstration is more or less an exact analogy for an orbit around a star. But how does this apply to light? So you can think of stars as really dirty light bulbs that are trying to trip me on the stage. So there's a light source underneath, and there's a bunch of crud on the surface. And that crud is various types of elements, everything from hydrogen and helium and things you'd expect to things like magnesium and uranium and all the other that you can find in the periodic table we see on the surfaces of stars. So when you collect starlight and put it through a prism, you can spread it out according to its color, and then you can take a photo. And this is what you will see. So if you look in really fine detail, starlight is riddled with these features. It's the dirt on the light bulb. And what you'll see in this case, although there's no chance this will show up. All right, here we go, pool cue time. So I've illustrated on here in red one of a particular chemical fingerprint, in this case magnesium. And so you can actually use a spectrum to identify what a star is made of. The other important feature is that there's a lot of sharp features that you can track. So if you have a star with a planet orbiting it, you might see something like this. So the spectrum with those recognizable features is actually going to change color in lockstep with the orbit of, and what you're seeing here is the Doppler effect on the light on the star. For this demo, I've actually exaggerated it by about a factor of 100 compared to what you would see for a typical exoplanet. But you actually do see movement that's this obvious for a star with a smaller star around it. And the takeaway point here is, so as the star is moving towards you, the light becomes bluer. As it's moving away, it becomes redder. We call these blue shifted and red shifted. And you can use these shifts to infer the presence of an orbit. If you see it going back and forth, that basically indicates there's two things going around one another. That takes us to what I actually do all day. So we are building a device, a high-resolution spectrograph called the Network of Robotic Shell Spectrographs, or NRES, at LCOGT. This is a diagram of how it looks on the optical table in our lab. And what you see here is a bunch of fancy optics and the prism that I promised would be there 3 slides ago. And the way it works is light comes in the side up here, goes sent by a mirror through the collimator, it goes through the prism twice, and there's a detector at the back. And it sees something like this. If you could put your eye where the camera is, it spreads the light out in 2 different dimensions and gives you a really high resolution picture, with enough resolution so that I can make the plots that I already showed you, and you can see the star moving back and forth due to the presence of planets around it. So here's a map of the LCOGT network. For those of you that are unfamiliar with us, we operate as Griffin already said, a global network of telescopes. They come in a variety of different sizes. The NRES spectrograph is going to be attached to our 1-meter telescope. So these are telescopes that are about the size of a car or a small SUV. And we already have them in the field in Texas, Chile, South Africa, and Australia. We're adding 1 in Israel this year and 2 in Tibet next year. The advantage of doing something like this is that you have 24-hour coverage of the nighttime sky. So things never set on our network. The idea is the sun never rises on all of our telescopes. So if something happens, you can see it at any given time. Or if you want to watch it for more than, say, 8 hours at a time, you can do that too. You can follow it from site to site and get the data that you want. People have made spectrographs like this before. It's not new in that it is a spectrograph that is high resolution and has this capability, but this is the first time anyone's ever made 6 of them and thrown them all around the world in a configuration like this. This is a photo of what our setup looks like in Chile. We've got 3 domes and a central building filled with servers and other goodies. And then this is an example of one of our telescopes here on the right. It turns out that to actually measure light with enough resolution to find transiting exoplanets, you need astonishing environmental stability. Maybe not astonishing, but it's really, really good. It's much better than what you get with an air conditioner. What we need for our instrument to work properly is something like 1/100th of a degree stability over like 10 years, or as long as we can get. But we've built a system, a completely separate, we built an enclosure for each of our spectrographs. They live in this thing called the igloo, which is basically a modified shipping container, a refrigerated shipping container that has air conditioning in the main compartment and then this neat plastic tent with fans that moves air around, and the spectrograph is installed in here, and the spectrograph itself lives inside like 3 layers of unobtainium or lead, or it's really thick, and it takes forever to change temperature. But long story short, we're actually going to be able to. We're actually beating our specification now, and we're going to be able to do everything that we want, and hopefully find sort of Earth-sized planets in 1 or 2 week orbits around typical stars. This is what it looks like if you're ever in the Galita area and are interested in seeing what telescopes, like what some of our telescopes look like. We have one in the back parking lot. We actually use that as our symbol. It's not on the map, but BPL is what we call it for back parking lot. This is what this white sort of rectangle cube thing is, the NRES igloo from the outside, and then it gets attached by an optical fiber to the telescope in the Solar Dome. And this project has been ongoing for several years, and we are nearing completion. The first unit we expect to install in the next month or two in our back parking lot, and then deploy to Chile in the fall of this year, and begin science operations immediately thereafter. So once available, this instrument will represent something like half of the world's capability in radial velocity at this precision level. So this is not a small undertaking. It was financed by the National Science Foundation but yeah, we're super duper excited about this, and we're really looking forward to getting these things into the field and seeing what they can do. All right, that's it. I'll stop there.
Thanks, Rob. So I'm sure you have lots of questions. Man, I thought it was just him pressing the buttons or something, but I guess it's real. Okay. So it turns out you are competent. Huh? So, okay, we're going to take a short 5-minute break. If you still have questions about Rob's presentation, text them to this amazing phone number, and we'll answer them after the break. So let's give Rob another round of applause.
Okay. We got a lot of really good questions, actually. This is great. Thank you for sending questions. We're going to have Rob answer a few here. You can take the other mic if you want. Okay, so first question is, so there are a few related questions about when did we first have the technology to detect exoplanets? Why are we finding so many now? Could people have found them earlier if they knew what to look, or is it a technology thing that's happening now?
Okay, that's a really good question, actually. So it depends on the method, but in particular, the transiting exoplanets, we did not know they would exist until just a few years ago. Okay,
yeah, let's repeat. The question was, why are we now finding so many exoplanets? Is it a technology thing, or could they have done it sooner if they knew what to look for?
So in the plot I showed with the huge increase in recent years, most of that was due to a $1 billion spacecraft that got put into orbit around the sun that was specially designed to find these things and found thousands of them. People, I guess 20 years ago, people were really wedded to the idea that our solar system was common and that large planets only occur really far away from the star. We now sort of believe that they need to form there. It's got to be really cold, or else the sort of lightweight gases cannot congeal into a planet. But it turns out that planets actually migrate and they find their way in really close to the stars, which is something that we haven't yet figured out. So I guess the roundabout answer to that question is we've had the technology to measure the brightness of stars to the necessary precision for something like 20 years or 15 years, but no one thought to look for these things because people were guided by their understanding, by what they thought was out there. And it turns out that nature had a whole bunch of surprises in store, and the first things that we started to find were actually radically different from the solar system that we live in.
Okay, so another great question we got is, for transits, is the size of the shadow and amount of light enough to identify the size of the star, or maybe they mean the planet? Don't you also have to know the distance between the objects?
So that's a really good question. So for our purposes, stars that are not our sun are sufficiently farther away that the planet and star are essentially the same distance. You definitely do need to know the relative distances of the planet and the star when it's close by. Like if you were looking at the transit of Mercury or the transit of Venus, those look different to us on Earth than they would to someone looking at our solar system from really far away. But you don't actually need to know the relative distances when you're looking at a faraway system that has both the star and the planet. You do need to know the size of the star independently or semi-independently, and we can actually do that by looking at the spectrum. By looking at the chemical fingerprints that are present, we can infer the temperature and the pressure at the surface and pin down the type of star to something that actually occurs in nature, and then you can back it out that way.
Okay, another one is why do you need the such narrow temperature tolerance? What part of the instrument requires the temperature to be so accurate?
Oh, that's a really good question. So when the temperature changes, the density of the air changes and the index of refraction of the air changes. So it's actually the air inside the instrument itself, when it changes pressure or temperature, changes the direction that light travels through it. It's like if you held up a glass filled with water versus an empty glass. That's an extreme example, but they're basically when the number of molecules the light hits as it travels through, like this fish that I just did with my arm, when you change the number of molecules in there and how close together they are, you change the trajectory of light through the instrument, and you effectively make it a slightly different instrument. And ultimately, what limits our precision is the fact that we're going to do that we calibrate the instrument by running a special super fancy lamp at the same exact time, and it travels on a slightly different light path. And we need to hold the temperature steady so that the difference between the calibration light and the science light is the same when we're observing the star as when we took our calibration data 12 hours before.
So Rob keeps saying good question. It sounds like he's complimenting me because I'm asking the questions, but I'm just reading the questions that you guys sent, which are really great, and I just wanted to remind everyone of that, because the next one is that container where you sleep?
That's an excellent question. That's an excellent question. Not yet. In Tibet, probably, due to lack of oxygen, and I don't want to die. It's like a balmy 68 degrees in there, so it's pretty reasonable if you have like a sleeping bag and a nice pillow. So
Okay, let's do a couple more science questions. Does the Doppler effect detection require the edge-on-orbit orientation as well?
Excellent question. No, it doesn't require it, but there's a tremendous synergy when it is edge-on. So if you can do the Doppler effect, if you have your orbit and it's inclined, you see less velocity. You only see the component of the velocity that's along the line of sight. So if it's face on, and in the planets, if you are the observer and the orbit is happening this way, you will see no radial velocity. You will see nothing. If it's this way, then it's maximum. And so one major drawback that I didn't talk about of the radial velocity method is that without some if you don't know the inclination of the orbit on the sky, you actually don't know the masses of the objects involved. So it could be, a planet that's pretty close to edge on, or it could be a star that's really close to face on. And those look exactly the same. But if you have a case where it also transits, you know it's edge on, and you can actually figure out exactly what that orientation is, because the time it takes to cross the face of the star is actually changed. So if it's dead on, perfectly edge on, it's traveling across the equator of the star, which is a longer distance than if it travels across a chord sort of near the top. And so you can tell from a combination of how long it took to get across, how fast it's getting around, and what the spectrum of the star looks like, what the whole system is. And you can eliminate all those uncertainties.
Okay, so we have a lot of really good questions. We'll do just one more, and I apologize if it's not your question. We just are short of time. But the last question a few people asked are, why are the orbits of the planets in our solar system all on the same plane? And does that mean it formed all at the same time? And is the fact that Pluto is in a different plane mean that maybe it formed later?
Possibly. So the short answer is yes. The fact that all the orbits of the planets seem to be flat, we understand to mean that our solar system, that all the planets in the solar system basically formed out of a pancake of dust and gas that formed around the star. And they congealed in that, and that's why they're all going the same direction in a really narrow range of alignment. Like they're all good to within 2 or 3 degrees, maybe 5 degrees for some of the holdouts. But yeah, so we do believe that they formed basically at about the same time, all from more or less a frisbee of dust and gas swirling around the very young sun. Pluto, it's less clear. It may have formed from that early, in that early mess, or it may have formed later, or there's also a whole bunch of other options. Like it could have, it's sort of being shepherded by Neptune, and it's possible that some of the bigger planets actually muscled it around and moved it into a different orientation than it initially started in. So.
Okay, let's thank Rob one last time.
And don't forget, if your question wasn't answered up there were a lot of good questions. You're welcome to ask Rob later. That's the whole point of this event, is that he's going to be wandering around afterwards, and he says that you're welcome to pester him. So.
Okay. Did he take the clicker? The slide thing.
Oh, Rob, give us back the thing for the slides.
Oh, no, it's here. Sorry. Okay, we're going to do our Astronomy in the News, which we do every month. We're going to go over some stories that were in the news in astronomy, and the media does not always do an excellent job in describing astronomy news. Sometimes they do. So we want to tell you some stuff we thought were interesting. So one of the first thing that got a lot of media attention was Mars this month. Here's the orbit of the Earth and Mars around the Sun, and Mars was in what we call opposition. So it's exactly on the other side of Earth compared, the other side. We have Sun on one side and Mars completely the other side. So when a planet is in opposition, you see it rise when the sun sets, and you see it set when the sun rises. And then that's also when it's almost as close as it'll get to us. It happens a little bit later because the orbits aren't perfect circles, they're a little bit elliptical. So a little bit later, Mars was in its closest approach to Earth for this year. Okay, people made a big deal out of it, but it was 46.8 million miles. That's the closest approach. Next year, it'll actually be 35.8 million miles, in 2018. So in 2 years, it'll be a little bit closer. So if it's closer, you can see it a little bit brighter and a little bit bigger, okay? But just to understand the proportions, this is a simulation of how big Mars looked in the last couple of weeks and will look in the next month. And this is the moon for scale here, okay? So it looks a little bit bigger if you're looking through a telescope, but you really can't notice it when you're looking by eye. Mars is about 150 times smaller than the moon. And so it's a bit annoying that every single year this comes up. Don't forget, Mars is going to be as big as the full moon. I can't wait. This is going to be every year, like August 27th. And this is never going to happen. Okay, but it still comes back every single year. Okay, so just please. It's so common that August 27th has become Mars Hoax Day. Okay, so if you see this, please do not forward this to your astronomer friend. Okay, we've seen this so many times. It's not going to happen. This is more like what it looks like. Okay, you can't see it, but it's there. I'm telling you, it's there. I think it's smaller than one of these pixels.
It's smaller than the LEDs on the screen, so it's.
But that's like even in the closest approach. Okay, so I was especially annoyed this year because now this happened. Okay. Again, this is never gonna happen. Okay. If this were to happen, two things would happen. We'd have incredible surf, okay, because of the tidal forces from the planets. The waves would just be insane, and we would all die. Okay. So it's not gonna be very amazing to look at. Okay. It's first because it's not gonna happen, and if it could, that would be very bad. Okay, but what did happen this time, so the Hubble Space Telescope was able to take this picture of Mars from Earth orbit during its closest approach. So that little increase in size is great for the telescope, and this is, I think, a fantastic new image of Mars that the Hubble Space Telescope took a couple of weeks ago. Okay, moving on.
The other piece of news was, you may have heard and seen trending on Facebook or whatever, that the Kepler telescope just discovered a bunch of new exoplanets. This is actually the same plot that Rob just showed in his presentation, but his stopped at 2014, which is right here. And you can see that this big yellow bar, what was discovered, or what was at least announced just a couple weeks ago, almost 1,300 new exoplanets were discovered in one shot with this paper that came out. And this is actually the first time that they did some special new statistical technique to just confirm that, based only on the transit light curve, which is what you're seeing right here, that these have at least a 99% chance of being true exoplanets. That's the best they can do with the statistics. But there are even another 1,300 probable exoplanets from that batch that could be potentially confirmed by other techniques. For example, that instrument Rob was just talking about that he's building could be used to confirm these other 1,300 exoplanets. So can you go back to the last slide, actually? The amazing thing that I want to point out about this is this field, when I was born, this was not a field. There was nobody studying exoplanets, at least in any earnest. And just in the last 5 years, we've discovered thousands and thousands of them. I think it's really amazing that we've done that.
Yeah.
Yeah, go science.
Okay, so yesterday, this amazing picture, this is a real picture of Venus, came through yesterday. It was taken by a Japanese satellite that got there, and then Rob pointed me to this picture. This picture appeared on the Astronomy Picture of the Day website, which is really great, and I recommend, it's a good way to start your day with an astronomy picture. But Rob pointed this out to me because he read in the caption that it said, "The satellite entered orbit around Venus late last year after an unplanned 5-year adventure around the inner solar system." It's like, wait, what? How does that happen? So we did a little digging, and it turns out on December 8th, 2010, so 6 years ago almost, this satellite was supposed to go into orbit around Venus, but it missed. What happened was, tragically, it was supposed to reach there. It reached Venus on December 6, 2010, and then it was supposed to slow down to get into orbit. So to slow down, they turn the engines on. They do what's called a burn. The burn was supposed to last 12 minutes to slow it down. In reality, it stopped the burn after 3 minutes because there was a problem with the engine. So it didn't slow down enough. So it just kept going. It didn't go into orbit. It just got flung around Venus towards the sun, which is not, not what they had in mind. So it actually got much closer to the sun than it was expected to, but amazingly, it survived, and it was going around the sun and Venus for 5 years until a couple months ago, they realized they have a chance to get it back into orbit using their little auxiliary motors. So in December of this year, they were able to do a tiny burn that got it back to where it was supposed to be almost exactly. This is not a cartoon drawn by a 2-year-old. This is the actual orbit. So it came in there. It's called Akatsuki is the name of the satellite. So it went into orbit. They did this little burn, and then they did again. And 2 weeks ago, it went into their final orbit around Venus, almost as originally planned, and started sending data. And no one expected this thing to come back from the dead like that. And their press release, so the last sentence, I don't know if you can read it, says the Akatsuki is in good health after Venus orbit insertion. Which is a very modest way of saying what just miracle just happened here. Okay, imagine it's like you're driving down the freeway and your exit is coming up and you start hitting the brakes and they don't work, so you miss your exit, and then you leave your car because there's no point anymore, and it just is driving around the freeways of LA for 5 years, miraculously not crashing into anything, not getting towed. And then suddenly you realize, oh, it's back near my exit again. So you get into your car and you use the little handbrake, and it just goes down the exit, parks in your house, and you're done. That's what happened to this satellite. So I hope we can expect more marvelous pictures of Venus coming up. And it's actually really important to study Venus because Venus is very similar to Earth, except it had a huge global warming effect, basically, a greenhouse effect, and that's why it looks so different than Earth. So it's slightly closer to the sun, so the temperature created a greenhouse effect, and we're trying to study, this satellite will study the weather on Venus and why exactly that happened, and maybe that'll help us avoid doing that to our own planet here if we can understand better the physics of what these kinds of things do to planets, and Venus is a great way to study that. So it's actually a really important mission. Okay,
so this was the other, I just find the news articles by just whatever's trending on Facebook. I don't know if it's the same for you and me, if it just thinks I'm an astronomy nerd, so it shows me this stuff. But there was recently this headline that the universe is expanding like 6% faster than we used to think. So that sounds incredible, right, if you don't know anything about it. But I'm going to, unfortunately, have to convince you that it's not as big a deal as it sounds like. So the first question we have to ask is, how do we know that the universe is expanding? So bear with me while I explain this. We know the universe is expanding because we see all of these galaxies far away from us, and they're all moving away from us. And it turns out that the galaxies that are further away from us are moving faster than the ones nearby to us. So what that means is, the nearby stuff is going away slowly, and the far away stuff is going away quickly. So the whole universe is expanding from the initial Big Bang. Then you have to ask, how do we actually know how far away all of those galaxies are? So the way we know that is, well, one way that we know it at least, is by studying a certain type of supernova, which is what I study. These supernovae are all the same brightness. So imagine you have 10 100-watt light bulbs. Okay, we don't actually have 100-watt light bulbs anymore because they're all CFLs now. They're like 18-watt light bulbs, but 100-watt equivalent. So imagine you have 10 of those, and you have them spaced out. Some of them are close to you, some are far away from you. So those far away ones are going to be fainter than the ones close to you. But you know that they're all intrinsically the same brightness. So that's the same thing with supernovae. You know that they're all intrinsically the same brightness. So the ones that are far away are going to be fainter than the ones nearby. So that's how I forgot this doesn't work. This last step over here on the left is showing you that all these supernovae are at different distances from you, and so therefore you can measure the distances to those galaxies. But in order to calibrate the supernovae, because you don't know exactly the absolute distance scale, you need to use these stars in nearby galaxies called Cepheid stars. They also have some intrinsic relation between their pulsation rate and their brightness, so you can kind of figure out how far all those galaxies are that have the Cepheid stars. and then you can transfer that to the supernovae, etc. So basically, it's complicated, but all that happened in this recent study was that they studied a bunch more of these stars with the Hubble Space Telescope. They got like, I forgot the number, like 100 of them instead of only 20, something like that. So that changed the rate of expansion that we calculate from looking at supernovae. The interesting thing here is that this isn't the only way of knowing how fast the universe expands. You actually, some of you probably have seen this picture before, which is a picture of a baby picture of the universe, the first light that got to us from the Big Bang, from the Planck, another space telescope right there. And I won't go into the details of how that works, but if you measure the expansion rate with that satellite, it actually comes up with a much different number than the supernova rate. And you can see here that these are all different numbers, the center point, all different ranges of what we think the expansion rate could be. And as we go up, sorry, it's hard to read the words there. The top one is the most recent one. We've narrowed it down to a smaller range than we used to know. But we think that if we understand physics, this expansion rate and the one from the supernovae should eventually reach the same number as we get more and more accurate. And it turns out that's actually not happening. They're getting farther away from each other. So that means there's something we really, truly don't understand. And we're going to eventually figure out what that is, but not yet.
Yeah, and that's great, because we still get to keep our jobs.
Yeah, that's how science works.
Yeah. Okay. Next story, you might have heard the International Space Station. So this is not a science fiction film. This is a real picture of an astronaut on the International Space Station on this part that they call the cupola, which they put with windows on so they can look at the Earth. So they're in orbit around the Earth. And this happened. So this is a marble-sized chip appeared on the window of that. And initially that's pretty terrifying. You don't want your window chipped if you're in the International Space Station. But turns out NASA said it's not a problem, it's safe, because these things are quadruple glazed. So there's no danger to the space station. But it's important to know what made this. So this was made by a piece of space debris, a really tiny little piece of space debris that's just floating there and hit the station really fast. And it had enough energy to make that crack. So there are actually over 170 million pieces of space debris that are smaller than a half an inch. And each one, if it were that size, this thing was much smaller, but if it were half an inch, of which there are 170 million, it could have done damage to the space station. That can disable a satellite, for example. There are about 670,000 objects that are between 1 and 10 centimeters in size that could have penetrated the space station. And there are a few tens of thousands of objects bigger than 10 centimeters in size, and if that hits the space station, it'll destroy it. Okay, think the opening scene in Gravity. Okay, that's what space debris can do. That's actually what it did. So this is actually a map of all the pieces of space debris that are orbiting the Earth. There's a lot of them. Humans have launched almost 5,000 things into space, and so eventually, sometime, it completes its task, and then they just leave it there. And sometimes these things collide with each other, and then they turn into a ton of little pieces in different orbits, and that's the really dangerous part. So actually, in our observatory here in Goleta, we're monitoring objects in space, satellites, to see if they're in a collision course, and then help avoid that, because that'll create more space debris, which is really dangerous for other satellites and for the space station. Okay, finally this happened.
My favorite story of the month. So some of you, anybody from LA here? Okay. I'm sorry for you, but so you probably noticed a few years ago that the space shuttle Endeavour was driven across LA to get from where they flew it in at the airport at LAX to get to the California Science Center in Exposition Park. And that was actually just part one of their eventual exhibit they're going to have there. Part two happened a couple weeks ago with this monstrous external fuel tank that goes on the shuttle being driven from a barge in the harbor across the streets of LA to get to the Science Center. I went down to see it. Here's a picture I took from right underneath it. It's really, really enormous. 65,000 pounds empty. If you actually fill it with fuel, it weighs 1.7 million pounds. And the eventual setup is going to be like this, where they have the actual flight setup for a space shuttle. There's the Endeavour right there in the front with the orange external fuel tank, and eventually they will bring in the 2 white solid rocket boosters on the side. And their plan is to build this ramp that goes around them, so you can actually go up and see up close all the different parts in their original configuration as they would have been on the launch pad. So this is just a note to any movie producers or whatever. If you need some crazy escape scene where like there's a space shuttle just ready for launch, sitting there, and you have your people running around trying to find it, this is the only place in the world where the full original flight hardware will be in Los Angeles. Of course, you still keep in mind you have to like fill it with fuel and everything, so don't do one of these stupid movies that makes no sense when you actually just show up there and
it's gonna happen. You know, there's
it.
gonna be a movie.
I'm sure this
about
is gonna happen. So the reason I'm saying this is that I will be credited with the prediction that there will be a movie where somebody tries to take over the space shuttle.
Okay, we're gonna take another 5-minute break and come back with our second presentation. Don't go anywhere. We have great food for you here, so if you're hungry, you can get some food and get some drinks, and we'll be back in 5 minutes.
Okay, welcome back. We're past halftime now. So it's my pleasure to introduce our next speaker. If you guys have been to the previous events, the previous Astronomy is on tap, you've seen her already at least twice, right? I guess there have only been 3 of them. So yeah, you saw her twice already. Charlotte Mason, who is one of my fellow grad students at UCSB, and now also at UCLA. And my interesting fact about her, I don't know if it rivals Rob's desk, but she looks like a cool person, but she has this secret inner nerdiness about none other than Harry Potter. She doesn't know I have these pictures, by the way. She once built the entire set of all of the Lego Harry Potter, Hogwarts, etc. This ship thing, I don't know, whatever, the dragon, with, notice here, the custom painted background with the mountains. So in addition to astronomy, you can ask her anything you want about Harry Potter after her talk. And here's Charlotte.
Okay, I don't know if I should thank Griffin for that.
Yeah.
Cool, okay. Yeah. All right, thanks, guys. Okay, so the thing that they didn't tell you is that I'm a time traveler. And tonight, I'm going to tell you some of my secrets. So I'm going to tell you about how using telescopes as my time machine, I can travel over 13 billion years through the history of the universe and to see some of the first galaxies forming in the universe. Okay, how do I do this? How can I travel in time? So we can do this because light has a speed limit. So the speed limit of light, if I'm converting everything here to American units for you, I'm doing my best. Okay, so the speed limit of light is nearly 700 million miles per hour. So that's a really, really high speed. But space is really, really, really big. So it takes light time to travel through space. So let's think about the closest big thing to us, the sun. So the sun is nearly 93 million miles away from us. Does anybody know how long it takes light to travel from the sun to Earth? Anyone? 8 minutes, all right. You're good, guys. 8 minutes. Okay, so when we look at the sun, we're seeing the light that was emitted from it 8 minutes ago. So we're actually seeing back in time 8 minutes. We're seeing the sun as it was 8 minutes ago. All right, so let's go further out. What about the nearest star? So the next nearest star after the sun is a star called Proxima Centauri, which you can see from the southern hemisphere. And it takes light 4 years to travel from Proxima Centauri. That's our nearest neighbor. Okay, so that's just within our galaxy. What about the next galaxy? The next closest galaxy, big galaxy to us, our galactic neighbor, is the Andromeda Galaxy. This is a big galaxy. It's about the same size as the Milky Way, and you can see it in the sky from Santa Barbara. Like, you can see it in the winter. It's like a fuzzy blob. Most things look like fuzzy blobs. It takes light 2 million years to reach us from Andromeda. That is our closest big galaxy nearby, 2 million years. So when we look at Andromeda, we're seeing the galaxy as it was when like mammoths and saber-toothed tigers were here on Earth. That's how far back in time we're looking. So you might ask, how far back in time can we go? Can we go right back to the beginning? And this is, I think I share this with Rob, like one of the reasons why we do astronomy is because we want to know, like, how did we get here? How did the first stars, how did stars, galaxies, planets form? How did we come to be? And one of the things we can do is look back in time by looking at light that's traveled across the universe to make a picture of how the universe has changed over time. So how far back can we go? Well, the universe is really, really old. There's a lot of big numbers in this talk. The universe is nearly 13.8 billion years old. So let's try and scale that down to a time scale that we're more familiar with. So let's imagine the universe, we scale it down to be like 30 years old, so a sort of human time scale. Okay, so for reference, the Earth formed about 4.5 billion years ago. So in our human time scale, that's like 20 years old. So when you're in college, the Earth formed. Okay, so what about the baby photos of the universe? So Griffin, which is great actually, I don't have to explain this too much. Griffin showed you the baby photo of the universe. So this is the cosmic microwave background, which is like a map of what the universe looked like. On our human time scale, it's 7 hours after the Big Bang. So just the first 7 hours of the universe. So it's actually nearly 400,000 years in real time, but it's a sort of real baby picture of the universe. And we see this image, it's the first light we ever see in the universe. Because before that, everything in the universe is like a really hot, dense plasma. All the particles are like bumping into each other, and light like physically cannot get out. But once everything in the universe has cooled down enough, then atoms can form, and this light can travel across the universe. So after the Big Bang, and after everything's cooled, we have a gas of like hydrogen, mostly hydrogen and helium atoms, and then a whole lot of dark matter. And then the universe is pretty boring for several 100 million years. So what is happening inside the universe during the first few 100 million years is that gravity is gradually pulling things closer together. And what we're going to try and look for are these first things that have been pulled together to form the first stars and galaxies. So we can model this in simulations. So this is a computer simulation of the first galaxies forming in the universe. So as gravity is pulling the dark matter and hydrogen atoms closer and closer together, we can fly around this simulation as time is passing, and you can see they're clumping together, and these will be forming the first stars and galaxies in the universe. Okay, so this looks awesome, right? This is, yeah, we want to see this for real. You don't want to just look in a computer. So can we see this? Can we just point our telescopes out and look for the universe, look back into the universe and see this? Well, actually, no. So the universe suffers from a problem similar to what we have in Santa Barbara this time of year. So there's a sort of cosmic June gloom in the universe. So this is caused by all of the hydrogen atoms that formed after the Big Bang. They're just floating around, not really doing anything, but they're blocking out any light coming from those first stars and galaxies. So the universe is just shrouded in this fog of hydrogen. And that means that we physically cannot see the first stars because they're hidden behind this fog. But just like how the sun gradually burns off our marine layer, galaxies, once they have enough stars in them, can gradually burn off this fog. So this is another simulation of the first galaxies that are growing inside this fog. So the black is the fog, and then the bubbles are where you see the first galaxies forming, and they are literally blasting away this fog. So this is when the universe is a bit like a Swiss cheese. So this is a really important thing for the universe. This only happens once in the lifetime of the universe. But if it didn't happen, we wouldn't be able to see other things in the universe. We wouldn't be able to see other galaxies. So it's a really important thing. So what I do in my research is try to understand how galaxies are doing this blasting. So I'm trying to look for these first galaxies and as well, look for them with telescopes and then come up with models as to how they're actually interacting with their surroundings and clearing out the hydrogen fog. And also, simulations are awesome. I wish things looked as nice as that when you look at them in a telescope. Okay, so if we're going to try and look for these first galaxies, what should we look for? What does a galaxy look like? Well, galaxies look like all sorts of different things. So this is a very small sample of things that galaxies can look like. I might have to get my thing out. Okay, I have to not hit the thing. Okay, so this is the Andromeda Galaxy. This is our closest neighbor. And then it's a nice spiral galaxy like the Milky Way. We also have some other spiral galaxies. This is a spiral galaxy, the Whirlpool Galaxy. Galaxies can also be elliptical galaxies, like this yellow blob. So this is really just a big ball of stars. They're generally older galaxies. Galaxies can also be interacting with each other. So these are two galaxies that are merging with each other. This is actually going to happen with us and Andromeda. The Milky Way and Andromeda Galaxy are going to merge in about 4 billion years. So, don't worry too much, but it's going to happen. And then you can also have galaxies that don't really look like anything very much at all. So this is a pretty nearby galaxy, but it doesn't have any discernible structure. It's a very small galaxy. It's just like blobs. Everything looks like blobs. This blob, this is actually the most distant galaxy that we've ever seen. So this was discovered by some colleagues of mine earlier this year. And it's a galaxy that exists 13.4 billion years ago. So this is the furthest back in time that humans have ever been able to see. So, pretty incredible. But how do we find galaxies like that? If galaxies look like all different shapes and sizes, what do we know? How should we know what to look for? So we can use the fact that galaxies are made up of... wrong pointer. Okay. Galaxies are made up of billions of stars. So just like Rob was telling you about how we can look at individual stars to look for their planets, to look for galaxies, we can look at the light that's coming from all of those individual stars. So if we zoom in on a picture of the Andromeda Galaxy, what you're seeing, all that like fuzzy haze, is literally just billions of stars. So we can take, just like Rob is taking spectra for his one star, we can take a spectra of a galaxy, and the spectrum of the galaxy is going to be made up of the light from all of its stars. So a reminder, a spectrum is just like we use a fancy prism to break up the light into all of its components, and you can see that from a galaxy, if we look at the amount of light coming from it versus color or wavelength, you can actually pick out some features that it's like a signature of the galaxy. So for very young galaxies, which are the ones that I'm trying to look for because they are the first galaxies, they will have lots of young stars. And we know that young stars, because we can see them in our own galaxy, emit lots of ultraviolet light. They're really big and hot young stars. So they're going to emit lots of ultraviolet light. And they're also going to have some more normal stars, and those generally emit more like green and blue light. So this is the signature that we're looking for when we look for these distant galaxies. We're looking for galaxies with lots of ultraviolet light that shows that they have lots of young stars. But as Griffin just told you, the universe is expanding. So that means that as the light coming from those galaxies, when it gets emitted, as it's traveling along through the universe towards us, space has expanded, the universe has expanded. So that light is going to be stretched. So the light is going to be stretched from bluer to redder wavelengths. And this is redshift. And it's basically the same, a very similar effect to what Rob was describing when the star and the planet are moving around each other, except this time the galaxies and us are moving incredible distances away from each other. So what this means for our spectra is that when we look at our spectra of a young galaxy that was originally lots of ultraviolet light, it's going to be, as the light has traveled all the way through the expanding universe, that light has been redshifted all of the way to the infrared, all of the way through. Sorry, thank you for my awesome PowerPoint. Basically, the further back it's been stretched, the more it's been redshifted, the further away that galaxy is, the further back in time we're looking. So if we want to find the very earliest galaxies, we have to go more and more to the infrared. And this is really the signature that we're looking for. So we're looking for something that emits lots of infrared light, but no other type of light, just infrared light. And so to detect these, we need to use some of the most sensitive and largest telescopes that have ever been built. So I'm going to have a sort of telescope war with Rob here. My telescopes are really, really big. So for my research, I used the Hubble Space Telescope, the Keck telescopes in Hawaii, which are these two at the bottom here, which is they're jointly owned by the UCs and Caltech. And then I also use a European telescope, which is 4 telescopes, which is called the VLT, which literally stands for Very Large Telescope. So the telescopes, they're the biggest telescopes in the world. So they're the ones on the ground are 10 meters in diameter. So when we talk about telescopes being big, what that means is that they can collect as much light as possible. So it's a common misconception that telescopes are primarily used to magnify things. They're actually really just used to collect light, like light buckets. So just in the same way that when it's dark, your pupil will dilate to let more light in, telescopes are really, really big just to let more light in. So I need to let as much light in to my telescope as possible because the galaxies that I'm looking for are really, really, really far away. So they're going to be really, really faint. But luckily, Hubble is awesome. So Hubble can detect galaxies that are 10 billion times fainter than the faintest star you can see in the sky. So that is an incredible piece of technology. So Hubble is now 26 years old, and it's continuing to blow our minds. I think Hubble has really revolutionized what we know about the universe. Before we had Hubble, we could only see about halfway back through the universe's history. And now we're able to see almost back to the very first stars and galaxies. So I just want to tell you some awesome things about Hubble. So if Hubble was in this room today, so it's about the size of a truck, it would have the resolution capable of picking out an individual firefly in Athens, Greece. And that is how we can use it to find the most distant galaxies in the universe. And it's doing this whilst orbiting Earth at 18,000 miles an hour. So it crosses over the US in about 10 minutes, and it goes around the whole Earth in about 97 minutes. So this is a picture taken by Yair of Hubble crossing over Santa Barbara, so you can see it. I actually looked it up. If you stay up late tonight, you can see it pass over the east of Santa Barbara at 3:30 a.m. So if you want to see Hubble tonight, you can do it. So Hubble is awesome. It's orbiting Earth, and it's really revolutionizing our view of the universe, and it's been doing that for over 2 decades. So when we want to use Hubble to look for these very distant galaxies, one of the best things that we can do is just point it in one direction and leave it staring at that patch of sky for as long as possible. So the same thing is true if you're into photography, you want to take a photo when it's faint, there's not enough light. You're gonna have a long shutter speed. Just let as much light in as possible. So you do exactly the same thing with Hubble. So this is the longest exposure ever taken with Hubble. This is the Hubble Ultra Deep Field. And actually, I just recently discovered that the idea for the Hubble Ultra Deep Field came from my PhD advisor's PhD advisor. So he's like my academic grandfather. So that's kind of cool. He's this really awesome Italian man called Massimo Stiavelli. And he's all over Twitter if you want to follow an astronomer on Twitter. So the Hubble Ultra Deep Field is a tiny patch of sky. They picked the most boring patch of sky. It's about the size of a grain of sand held at arm's length. And they pointed at that patch of sky for over 10 days. And they found over 10,000 galaxies in that tiny patch of sky. So this is the real data from Hubble, the real image that was taken, and we're just flying through it. So as we fly into the image, we're flying back in time. Yeah, this is awesome. And so this is just this one grain of sand at arm's length. If we wanted to take a picture of the whole sky that was as good as this photo, it would take Hubble more than 1 million years. So we're probably not going to be doing that anytime soon. But just from this one image, and we take other photos that are similar to this, we can learn an awful lot about the universe. So one of the things that we've learned about the universe and about galaxies is that as we go further back in time, galaxies get smaller and lighter. So what I'm showing you here are, again, real images from Hubble. So on the right, you have images of galaxies that are closer by to us. So these are like galaxies today. And towards the left, we're going further and further back in time. So the galaxies are further away. And what you see quite clearly is that galaxies are getting smaller as you move further away or further back in time. So this is telling us that galaxies are growing. So that makes sense. You expect galaxies to be growing. They're getting bigger. And they're building more stars, so they're getting brighter, bigger, and heavier. One other thing that we've realized is that galaxies are producing more heavy elements. So after the Big Bang, we just have hydrogen and helium, and it takes stars and supernovae to form the first heavy elements. So basically everything in your body that's not hydrogen and helium was built in a star or a supernova. And we see over time those elements are being built in these galaxies. But one thing that we realize is that if galaxies are getting smaller as we go further back in time, there are an awful lot of really small galaxies that we can't see. I mean, Hubble is awesome, but it can't see really, really, really small things. So one of the things that we can do, and I'm part of a team that uses this technique to look for very distant galaxies, is to use gravitational lensing. So if you were here at Astronomy on Tap in April, you should all be experts on gravitational lensing, right? So Curtis explained gravitational lensing then, but the basic idea is that when you have a really massive, heavy object, like a big cluster of galaxies, so this, in this image, would be like the big yellow things that you can see. It's a big cluster of galaxies. They're so heavy that the gravitational well, they form a huge gravitational well around them, and that light traveling from behind them will get bent around it. So light traveling from very, very distant and back in time galaxies that are behind the galaxy cluster will be bent around the cluster as the light travels to us. And what that means is that the light from those galaxies will be distorted and magnified around the galaxy cluster. So you'll see like these arcs and all of these weird distortion effects. So this is a simulation of what would happen if you sort of tilted your head around a gravitational lens. But we actually can use this as a technique to start to find really distant, really faint galaxies. And I was recently part of a team that discovered the smallest early universe galaxy ever. And we did this using gravitational lensing. So this is all real stuff from Hubble. This is the image that we took with Hubble of the whole galaxy field. So this here is the gravitational lens cluster. So everything that's kind of orange in the image. And what we saw is that in 3 places around the gravitational lens, where these 3 white boxes are, we saw something that looked like a very small galaxy. You probably don't believe me at this point, right? Is there anything inside the box? Okay, so I'm going to zoom in. You probably, I don't know if you still believe me or not. So this is like the data that we get from Hubble. This is what we see. So yeah, I feel so like sometimes people are like, oh, you study galaxies, you must see like amazing photos. Like, no, I see like 3 black pixels. Yeah, I should be studying like all the things that are around the outside. But yeah, but this is a galaxy that existed over 13 billion years ago. So yeah, it doesn't look like much, but it's pretty amazing. Yeah. Okay, so so Hubble's really good at taking images like that, but it's not so good at actually taking detailed spectra. So they sent me to Hawaii last year, which was fun, to use the Keck telescopes. I don't know why, because I'd never used a telescope before, and I very easily could have broken it. But luckily, I didn't break it, and we actually took detailed spectra of these 3 patches where we saw a galaxy, these 3 boxes where we saw a galaxy. And inside those boxes, we saw the same spectra in all of them. So you can see in each of these 3 spectra on the left, they have a peak, and that all lines up in exactly the same place. So that means that these are all exactly the same galaxy. And in fact, it's just because of the gravitational lens, the light from that galaxy has been distorted so much that you see it in 3 different places. Just like, if you play around with a magnifying glass, you'll get distorted images. It's exactly the same thing happening. So it's the same 3 galaxies, it's the same one galaxy, but we see it 3 different times. And so one of the other things that we can do with the spectra is weigh the galaxy. So just because the spectra is made up of the light from all of the stars inside that galaxy, we can use the spectrum to make an estimate of how many stars are inside the galaxy. So we weighed the galaxy in this way, and we found that it was 5,000 times smaller than the Milky Way. So this is tiny. This, they claim this is the smallest galaxy ever detected at that distance. Or that far back in time. And we can do this just because of gravitational lensing. If it hadn't been gravitationally lensed, we never would have seen this galaxy. So we're getting to the point now where with Hubble we can detect these very distant galaxies, and then we use telescopes on the ground to go and we follow them up to check that they're really there. So I'm now running a program at the VLT, the Very Large Telescope, to look for nearly 100 galaxies that are similar to this, that are behind gravitational lenses, to check that they're really there. And then we're going to use the properties of those galaxies to help us understand what's really going on in the early universe, how these first galaxies are forming and growing, and how they interact with this hydrogen fog. But we're getting to the point now where we're limited by detectors. So we've done an awful... It's gone out. Okay. We've done an awful lot of amazing things so far. We've seen light that was emitted just 3%, when the universe was just 3% of its present age, but we're limited by our technology. So Hubble cannot go any further infrared. If we want to see further back in time, we have to go further infrared. And we cannot do that with Hubble. We can't go and repair it. Well, we could go and repair it again, but it's probably not worth it. And we cannot see things that are any fainter. We can't see those really small early galaxies. So we need to build bigger telescopes and ones that go even further into the infrared. So I want to end with just telling you a little bit about some of these awesome new telescopes that we are going to build, or are already building. So the first one is the James Webb Space Telescope. So I'm going to tell you a little bit more about that in a minute, but that is the successor to Hubble, which is launching in 2018. There's also going to be some new telescopes on the ground. So there's a class of telescopes which will be 30 meters in diameter, so that's more than 10 times bigger than the current telescopes we have on the ground. So one of those is the 30-meter telescope, which is a project with UC involvement. The Europeans are also building one. See if you can guess what they're going to call it. The European telescope is called the Extremely Large Telescope. So I think they need to come up with better names. And those also going to be going further into the infrared. And they're going to use a special focusing technique called adaptive optics, which will make everything like really clear. And there's also going to be a new class of telescopes, which I'm actually pretty excited about, which are radio telescopes. They're building this huge radio telescope in South Africa that's called the Square Kilometre Array. And these radio telescopes will enable us to actually see the hydrogen fog itself. So the hydrogen fog emits a very weak signal, which happens when hydrogen atoms basically flip up. The electron around the hydrogen atom is spinning, and it'll flip. And it sends out a signal that is a wavelength of 21 centimeters. And as this gets redshifted all the way through the universe, by the time it reaches Earth, it's in a radio wave. So we're going to be able to detect this in radio waves. It's technologically extremely hard to do because there is so much interference from radio waves on Earth. So if we can actually see past all of the radio that we have on Earth to see this signal coming from the very early universe, I think this is going to be amazing. We're going to be able to map out that hydrogen fog of the very early universe. Okay, I want to say a few words about James Webb because space telescopes are awesome. So this is now a telescope. This is a photo of the telescope at NASA Goddard. So it's now fully assembled. It is a telescope. It has its mirror. This awesome mirror is 21 feet across. You can see a little person down there for scale. And it's beryllium mirror coated in a layer of gold. It's not just because astronomers like bling. It's actually really good at collecting that infrared light. And so it's now fully assembled, and they're doing vibration testing to make sure it's going to be ready for launch in 2018. James Webb is going to be very different from Hubble in that it's going to be placed far away from Earth. So Hubble, as I said, is orbiting Earth. James Webb is actually going to be more than 1 million miles away from Earth. So it's going to be orbiting the sun, and it's just going to be kind of hanging out just behind the Earth. And we do this for two reasons. Firstly, the Earth gets in the way of Hubble a lot, so we want to just move away from the Earth. And secondly, it needs to be really cold. So a lot of things in astronomy need to be a perfect temperature. And especially for infrared technology, everything on Earth, everything that gets hot emits infrared radiation, and that's really going to interfere with our instruments. So you have to keep the telescope as cool as possible. So we're going to put James Webb 1 million miles away from Earth and then have an enormous sun shield. I'll actually show you that on the previous slide. So this funky thing underneath it is like a sun shield that's the size of a tennis court. And this is going to be pointed, this bit's going to be facing the sun, so just to keep the telescope as cool as possible. So if that all works, it's going to be awesome. We're going to be able to see in incredible detail the really far infrared, the really distant galaxies. If it doesn't work, we can't fix it. So I hope for my career's sake that it works. If it doesn't work, I don't really know what I'm going to do. Hopefully it works. But I think your take home from this should be that we've seen, billions of years back through the history of the universe. We're now at the point where we can discover some of the first galaxies forming the universe, and the future is very bright. So this is an example of what you might be able to see with James Webb. So on the left is the Hubble Ultra Deep Field. So this is the deepest image ever taken with Hubble, which I think James Webb can take in an hour. It could take that photo in an hour. On the right is what you could take with the James Webb Space Telescope. This is a simulation. You can just see, thousands more galaxies in that image. So James Webb is really going to, just as Hubble did, further revolutionize our view of the universe, and it's going to be really exciting. So hopefully in 10 years we can do another Astronomy on Tap, and I can tell you all of the awesome things that James Webb did. Thank you.
That was really great. So we're running a little bit behind schedule. I'm sorry. We're going to take a very short break, during which time you should text all of your questions to Charlotte about her talk to 805-55-AOTSB. I've been told by all of the Apple haters out there that you can also type the letters into an Android phone and it will still work also. So go ahead and text those numbers, all of your questions, and we'll be back in just a minute, at which time we'll answer the questions and do our very popular raffle of Astronomy on Tap prizes. So stick around. Okay, we're back again. Lots of good questions. We're just going to pick a few. And if you don't get your question answered, I'm sorry, we just don't have time, but Charlotte will be here for you to ask in person afterwards. So the first question is, doesn't the older light from the light from the older galaxies get corrupted, or does the light from older galaxies get somehow messed up before it gets to us? How is it that we're seeing so far back in time without things messing it up in between?
Okay, so yeah, that's a really good question. So in general, it's not really a problem because the universe is so huge that things are pretty spread out. So like when I showed you the Hubble Ultra Deep Field, it's pretty easy to see like that's a galaxy, that's a galaxy, that's a galaxy, and there's not really anything in between because the universe is so big. Very occasionally, things do get in the way, and that's often what we see with gravitational lensing when you have a really big galaxy in front of a much more distant, further away galaxy. And in that case, you do have to spend a lot of time trying to like disentangle the light from the two different types of galaxies. But often, because they're at very different distances, and two, because they'll probably be very different types of galaxy because they exist at different times in the universe, you can pretty much figure out which galaxy is which. So.
All right, the next question is, what object is forming the lens for Charlotte's triple imaged galaxy? Okay,
yeah, so in gravitational lensing, one of the times, you think like, just like, right, I have like one big thing, like one big sphere, and then there's something coming from behind it that's getting better around it. So that is our beautiful ideal version of what happens in gravitational lensing. But when you have like a galaxy cluster, you have hundreds or thousands of galaxies that are all clustered together, and they all will have their own individual gravitational field, and they're all going to be producing different gravitational lensing effects. So it's really just the fact that you have lots of different bits of the gravitational lens that are going to be giving you that extra distortion to produce the three images. So it's really messy. Actually, there are people who spend like their entire careers trying to figure out what the shape of these gravitational lenses is for clusters of galaxies.
Okay, here's one I really like because this was a question I asked when I first started studying astronomy. Are galaxies moving away from us greater than the speed of light? The implication being that, we know that things can't move faster than the speed of light. So how is that possible?
Okay, yeah, I get asked this question a lot. So technically, yes. So like that one galaxy I showed you that was the red one that says the most distant galaxy we've ever seen. So if you use the technical definition, that is moving 10 times faster than the speed of light, but it's not really. So the notation, like the maths that we use to say how fast something is moving does say that it's moving faster than the speed of light, but actually it's not because the galaxy itself isn't moving. It's space that is expanding. So the galaxy isn't really moving at all. It's just the space that is moving faster, yeah.
It's a very philosophical point to make,
Yeah.
but come ask us later if you didn't understand that. Okay. Lastly, do you make the simulations yourself?
Okay, so I didn't make any of the simulations that I showed you. I do more simple models in my computer, not as fancy as that. It's kind of an interesting point especially for a lot of people in astronomy, is that people get classified normally as like observers, who are people that go and look and like take photos of things, use telescopes, and then theorists who like think about stuff or make simulations or make models. And I tend to try and like bridge the gap. So I do like simple theory and simple observations.
Okay, one more that I'm going to answer, actually. So somebody asked, we talked about the 21 centimeter line, which is the line that comes from the hydrogen fog itself. Someone asked, what is 21 centimeters in megahertz? So I typed into Google, speed of light divided by 21 centimeters, and the answer is 1.4 gigahertz, or 1400 megahertz. So you can't listen to it on your radio. I assume that's why you're asking. It's too high for the radio frequencies. Okay, let's thank Charlotte again. That was really great.